So I am like interested in solving like problems. It will keep me up at night if they are hard and it feels like, oh, I don't know the answer to that, and let's try to find it out. So there are advances happening like everywhere to make this pipeline faster, and then the application came along. Like it's so amazing that I am making some sounds and you are understanding it and then you are responding it. Just if you think about it, no computers, just humans, the language. But now a machine can understand it and I can talk to a machine. We have normalized to this, but we don't understand how amazing that is.
I've learned that you're interested in comedy.
Yeah, and I think there is some correlation between like doing stand-up and computer science. When you're doing like a stand-up a bit, you want your audience to connect, so you are basically giving them a reference. And then the hope is they will get that reference and then they will fetch the value from that reference and they will feel accomplished, and that's where the laughter comes from. And your goal on a stage is to give them a reference that they can fetch the value for. If you give them the value directly, they will say, this is not funny. This is too direct. Yeah, that's how I got into it, and it's an interesting process. It did get me an upgrade one time.
What happened?
during a flight. So I was on sitting waiting for the plane to arrive at the gate, and then they delayed my flight a couple of times in a small increment. It was a Delta flight, so I posted on Twitter that so my flight got delayed multiple times in a small increment. I am flying Delta. I guess it's in their motto that we delay our flight one Delta at a time, and I tagged Delta and they replied and I got an upgrade.
In today's episode, we're thrilled to have Dr. Manish Gupta with us. Manish is a leading authority in AI training, GPU performance, and compiler optimization. Manish is currently at Magic, where he focuses on scaling test time compute, long context models, and reinforcement learning. Before Magic, Manish enhanced the performance of large-scale LLaMA models at Meta, led GPU cogen efforts at Google, and was an early engineer for Nvidia's Cutlass project, where he optimized gems and convolutions across many GPU generations. Manish holds a PhD in Computer Science and Engineering from University of California, San Diego, where he was a Powell Fellow. Manish graduated gold medalist in Electrical Engineering from the Indian Institute of Technology, Roorkee. We're excited to hear Manish's insights on cutting edge of AI training, GPUs, and inference. Manish, welcome to the show.
Thank you.
Manish, you have a PhD from UC San Diego and also graduated as a gold medalist from IIT Roorkee. How did you end up working on GPU programming and AI, and what was your journey there?
Yeah, taking me some years back. So I think my first exposure to GPU was in like grad school, first year in the compilers class. We picked up LLVM in a project using GPUs. At that time, I was not writing CUDA, but doing some static analysis on CUDA code using LLVM, where LLVM is a compiler infrastructure. This is 2010, I believe, and then LLVM stands for low-level virtual machine, and it's a compiler infrastructure to analyze and do transformations and generate code. So we were analyzing CUDA code and proving some things. And at that time, I was in love with LLVM and not so much with GPUs, but that was my first exposure. Then at AMD, I worked on AMD GPUs, again the combination like GPU and LLVM. At this time, I was not just analyzing, using the compiler infrastructure to analyze the OpenCL AMD code base, and then also generate some transformations. But I would say like real GPU exposure like happened my 5 years at Nvidia, and that's where it like I get into the the depth of how the GPUs work.
So at Nvidia, you were exposed to various GPUs, and then were you working on GPU programming right away, or was there a path that led up to that?
Like I looked at some of the libraries, and I was initially like part of the cuDNN team, and then I saw this Cutlass project brewing, and I looked at the code base, and I feel like at every point in your journey you have to fall in love with something. So in my PhD in 2010 I fell in love with LLVM and its code base, like how it was structured. Like you look at the compiler's book, I remember the Dragon book, and then the you will find an exact structure for that in the LLVM code base, and I just fell in love with that. And when I joined Nvidia, there to be honest, when I joined Nvidia, no intention of like doing AI. It was, I read a lot of stuff about matrix multiplication. As soon as I joined, there is a documentation inside which is called GEM for Dummies, and I think during my time at Nvidia I may have read it like 50 times. And the first time I read it, it's supposed to be 3-4 loops, M, N and K. There is so much that is going on, and I only got like 5 to 10% of that document. And then it became like I want to get understand it. So how do you understand it? And then I saw this project Cutlass brewing, and then like I could map the documentation, I could map the PTX to the part in the code base, and it was well structured. So yeah, I would say it began there, going into the weeds of GPU.
Okay. How about AI? When did AI come in?
So I am like interested in solving like problems, and if it will keep me up at night if they are hard and it feels like, I don't know the answer to that, and let's try to find it out. So I was working on understanding the GPU and how do I make matrix multiplication and convolutions and the other algorithms go fast on GPUs. And then there was a time, I guess 16, 17, 18, when AI became really hot. It was probably hot before that as well, but and then matrix multiplication was the core computation in there. So, and then there is not just about matrix multiplications, there are reductions and there are other things and other operations, but it's the core of your operation. So at that point, I think the algorithms around matrix multiplication became more going to the AI, and that's when the AI journey began. Yeah, I mean, matrix multiplication goes in many other things like physics, chemistry, signal processing, and then they will have their own variations. Like the inputs are coming, you are accumulating something, and then you are outputting the result, and then you're doing something more on those accumulations, or the inputs are being transformed in some way. But the core is that matrix multiplier, but then when it goes to AI, okay, now you have to think something. How do I fit this in the AI world? Like for one example is maybe to like flash attention is like there are two matrix multiplication and a softmax in between. Yeah, I guess that's how the AI came into the picture.
So as an interesting application or extension of the core concept of things like matrix multiplication.
Yes,
essentially.
Yes.
Okay. And before the experience at Nvidia, you had worked at Qualcomm, and then now you're at Magic. So you've worked at Qualcomm, AMD, Nvidia. You've also had stints at Google and Meta. How did each of these experiences shape your perspective on building GPU and AI solutions today?
Yeah, I would not say like all of that would go in like building the GPU and the AI experience, but yeah, all of these experiences have like an important role to play in shaping up my thinking and meeting these people on the way. So Qualcomm was my first job out of my bachelor's, and then I was doing programming in assembly. Like there was their QDSP 6 and 7 chips, and then they will give us the instruction manual, no compiler, no nothing, and this is the instruction, these are their wait cycles, this is their register, this is knob and how many knobs you need to get the operands after this instruction. You will figure all of that out through that manual, and then by hand optimize. We will have C or C++ code for like audio decoders and encoders, and C will be our reference, and we will write the assembly by hand.
So in some ways, you were like a human compiler.
Yeah, I
right?
was. I was the human compiler.
So you had C-level reference implementations, and
Yes.
then
Yes.
you took that and converted that to assembly.
Yes. So we were doing that. I think our code was going into RIM and Blackberries and all these phones, 2008, and then I think that led to the segue. Then iPhone came along during that time, and I had no intention to move to the US, and I looked at that, and then Qualcomm, and then UC San Diego, and then I said, okay, let's see what can be done, and then I wanted to learn more, and then how the master's and the PhD journey began. So that was Qualcomm. During my PhD, my first paper was GPU, and then I was in search. I think I had the beginner's luck in my first paper, and that got in first attempt, and after that I had like 6-7 rejected papers, and I think San Diego helped there. Every time I got a paper reject, I will go to Torrey Pines and look at the ocean. And you know that we were there together in UC San Diego, and you were the one who suggested that, like, take all of these work that is not going somewhere, and then I sent it to AMD and Intel, and then I went to AMD, and then I worked there for almost 10 months on GPUs and LLVM again, and I can go in detail of that if you and the audience is interested. And there at AMD, I think what I learned is that even in this was, I don't know, 2015 or 16, no, this was not AI, and all of this rejected work that I had questions on the data. Like, I was doing some random number generation for generating the data, and then how is that relevant for the problem you are solving? And then when I went to AMD, I got real data from their data centers. I was doing some reliability studies on the error rates, so I got the real data from their AMD data centers, and I could apply the same techniques or like modification of them now that I have real data and a lot of compute, and this is not AI, and I got like 4 or 5 patents, 3 papers in there, and I just figured then I need data and compute, and this was not AI. And I went back, defended Nvidia. I can go on lens on talking about Nvidia. There we worked on like these abstractions on how to expose this low level PTX and assembly to the programmer who don't know that, and still be able to write these operations and modifications of these operations, which is Cutlass and Qt. And then after I figured that this is good, but we want to do it more automatically, and then we could see that there's a really great project also in open, which is by OpenAI Triton, like OpenAI Triton, where you can do this not the way we were doing in Cutlass, but using MLIR. So then at Google, I got an opportunity to learn and try MLIR, and they wanted to write or generate code for GPUs the way they do it for TPUs. So imagine you're writing software for GPUs, but now imagine a software writing software for GPUs, and this is again not AI. The first software is the kernel, and you can write the kernel directly in, say suppose if you write the assembly directly, like I was doing it at Qualcomm, or you write in C++, which compiles to assembly or a PTX in case of Nvidia GPUs, or a software where the second software is a compiler that is writing your second software, which is kernels. So a compiler writing a kernel or generating a kernel, that's what I was doing at Google for Nvidia GPUs, and we were able to match A100 performance by generating these kernels instead of writing these by hand. And then I moved to Meta to see how these large scale deployments are happening on Nvidia GPUs. And then I recently joined Magic, where we are doing a lot of interesting new stuff, trying to make a breakthrough at inference time compute scaling. And
your early work then included a number of different things. For example, at Qualcomm, you did low-level assembly, and then you seem to have spent a lot of time doing compiler optimizations, and then in between came the work on reliability, where you had data from the AMD data centers and so forth. At what point did AI become the central focus of your career, and why did that happen?
Yeah, that's an interesting question. Like, I could have been doing something else, but I think the main focus is, again, like, you at every point in your life falling in love with some technology and just take where it takes you, like, at some point I fell in love with this project called Cutlass, and then we were doing these computations, and I have written like FP32 and FP64 gems as well, which is like double precision, which are not used in AI. So you can use this library to write computations that are not used in AI, a different data type, different ways of loading things. So the core concepts stay the same, but you are writing your algorithms for something else, or like convolutions as well. They go in CNN, but they also go in a lot of image processing and non-AI related areas as well. So at the core, I guess my focus has been always like solving interesting hard problems, and at some point the concentration of that problems is AI. So I guess naturally the AI became my focus. Like, if you look at all the like software, if like Nvidia creates or out in the open source, I would say, like, or at least I can say for this Nvidia's Cutlass library, I would say, like, this is my rough estimate, I would say like 92 to 93% of it will be all used in AI right now. So that's why anybody who's working in that area will naturally tend to go there, because the hardest problems are there.
Yep.
And then that's where I can make a biggest impact.
It seems that Nvidia's Cutlass is widely adopted by companies doing AI and building foundational models and training and so forth, right? Manish, I would have imagined the year is 2025 today, and matrix multiplications are such a fundamental computation. You would have thought that that's a solved problem, but apparently not.
Yeah, it's interesting. Like, when I joined and I read that Gem for Dummies document that I was telling you, is that is how I was astonished and surprised, and that got me peaked. By the end of this month, I want to understand everything in this document. And I set a very huge target, because month was not enough. I think if you give me that, there may be still some things in that document that I will miss, because it was so dense. And there is a lot that goes on, and it's not just about matrix multiplications, right? It is your core computation, but you have to build your software in a way that you can easily access the operands going into your matrix multiplier. Like, you're going from some memory into some intermediate memory, like share memory, and then some registers. Now on Blackwell, there is another level of memory in there, which they are calling tensor memory. So there are various levels of memory before the data reaches the matrix multiplier unit. And the goal is to get them there efficiently, and not just that, you should be able to access the data at each of these points efficiently as well. Because just before the matrix multiplication, if your data is in the registers, and just before it goes into your matrix multiplication, you want to do some data type conversion on the input data that you have read, then you should design your like software abstractions or your compiler infrastructure in a way that it can go in, tap in there, and then do that changes as well. So one is that I think that angle is coming from the programmability angle. But even if you just want to write plain vanilla matrix multiplication in GEM, like from the architectural perspective, there are still lot that you have to do to make it run full throughput, like to feed these math units so that they have the data to work on it, and then they are producing the accumulators and you're writing them out. So there is a lot. that goes into it to make them fast.
Okay, so basically then you're continuously adapting to the ever-changing world of hardware, right? Because the hardware is continuously shifting, right?
Yes.
Yeah.
I mean, that's what it is. It's 2025, and you can no longer get the performance. I don't want to say for free by scaling, like from 14 nanometer to 7 nanometer. You don't change anything in an architecture, and you are going to get more performance by just having smaller, less power hungry transistors. Now you either need to put in more transistors, or you need to change the layout of this transistor, or you have to put these transistors in a way that is different from the previous chip. So when you do that, you are introducing like humongous architectural changes from one generation to another, and then you have to expose them in your ISA, and then you have to, ISA is like the specification of the hardware, so you have to expose them in your software stack, and then how the low level programmer who knows this ISA will exploit it and build the abstractions on top of it, so that the higher level of stack can also exploit it. So yeah, there is a lot of architectural changes that are coming that anybody who's working in this field has to take care of.
So, you're doing all these optimizations and trying to be successful with it, but what is success? How do you define success? Being a AI programmer or a role level optimization person who's in charge of doing it, what is success in your role, and how do you measure the impact of your work?
Yeah, that's a good question. It's I mean, it's so simple, and everybody asks it every time it comes up, like what is the impact? I would answer it like, you have like a quantitative metric of success in specifically my field, or the field I am in right now, is that how much latency you can improve, like how fast can your computation go that your users care about, and are you operating on peak math throughput for the compute bound computations, and you're operating on the peak bandwidth for the memory bound computations. So that is the quantitative metric. The qualitative metric would be like, have you built your software abstractions in a way that you can read it the next time you open your code yourself, because your peers can read it who are in the same area, and then a success would be somebody who doesn't know these low level operations can exploit it. So there are two very good examples of these code bases from the Nvidia GPU perspective, is like OpenAI's Triton, and then Nvidia's Cutlass library, where you can see this happening. Like they operate at pretty, like Cutlass almost operates at the peak that you can get. OpenAI Triton also operates at very remarkable performances, and then it has very, very high programmability. Like somebody who doesn't know anything about Nvidia GPUs can just program in Pythonic format to exploit these new instructions.
Okay, so when you say peak capacity, for example, say a GPU hardware can support say a petaflop of performance, then you're approaching a petaflop or 90% of it.
Yes. For a large enough computation, like large enough matrices, you are reaching the peak, the theoretical peak. You're reaching close to it. Like for example, on Hopper for 16-bit, it's 989 teraflops, and I think the most efficient can reach close to like 785, 800-ish. So
approaching that essentially.
Yeah. And you see these shapes these days in training models, like these large matrices, these shapes, like used to be, this is just a benchmark, like where is going to be used. But now you do see these shapes, especially during the training time, you see these large matrices.
So how large are these matrices? When you say a large matrix, how large is large?
I mean, you can take a look at the LLaMA model, right? You like M, N, and K, like you can like of the order of 8K by 8K by 8K or 16K. There are some differences in like N and K, but 8K by 8K by 8K is sufficiently large. From the Hopper's perspective, you have to also think of how large are your matrix multiplier units. If they go bigger, your matrix have to go bigger to get the full throughput out of it.
Okay. And then, Manish, of course, what you said, you've done this work on GPUs, but then there are all these new architectures that people are proposing these days. There are other companies. Then I'm assuming all of these have to go through the same cycle of optimizing for that specific hardware, right? There's no free lunch available for them as well.
Yes. Yeah, there is no free lunch. You have to do the work. You have to do the hard work. You have to have performance. You have to have programmability. And you can get away with some programmability for some time for like these transformer models, because, and that's what has happened in my opinion, that this like since the release of GPT, these transformer models were released like in 2017 with attention is all you need, but they became kind of commercialized and like, oh, this is a real use. During when was ChatGPT? It seems like 2022 or 3 December. Yeah. So after that, these have not changed, and you can see that because something has to stay fixed. If you're programming, you don't have a programming model, then your model has to stay fixed. So that's what has happened. And these other like hardware vendors, which everybody wants to win, I want them to win. Cerebras and Grok, they have had this for the very first time. I guess the model stayed fixed, so they can create their software stack on something that is fixed. But if tomorrow there is, or even today, like there are some changes in the transformer model, like people want to try different variations of matrix multiplications, or different ways they want to exploit these tensor cores or these matrix multiplier units. Like flash attention is one way, like convolutions are also mapped onto these matrix multipliers. So if some, like back when convolutions were important, people were making specialized chips for convolutions. Maybe somebody still is, but Nvidia with their programmability was able to use the same GPU to do convolutions very, very efficiently. They've been able to use their same GPU to do flash attention very, very efficiently because of the programmability that they have. So all of these other vendors will have to create they have to have some sort of programmability in their software stack.
Yeah, understood. So any new AI player needs to manage that, and there's so many, right? There's, of course, a couple you mentioned, but there are apparently like more than 100 funded startups today, and then there's this whole world of edge AI as well, right? Where a lot of people are developing edge AI solutions primarily around inference, right? I think we'll talk about inference in more detail and current trends there in a bit. Manish, completely different offset or a different area I want to ask questions on. I've learned that you're interested in comedy. And what made you interested in comedy?
Yeah. I have not gone on stage for like, I don't know, 2-3 years. But yeah, there was a point I was like going on like every twice maybe a week. In a week. So during my like grad school, I took some improv classes to improve my presentation skills, and then I met some stand-up comics, and I liked the process of writing, and I got in writing, and then I liked that process, so I got into it, and then and I think there is some correlation between like doing stand-up and computer science. This is just my like in my thoughts is like when you're doing like a stand-up bit, you want your audience to connect, so you are basically giving them a reference, so that, and then the hope is they will get that reference, and then they will fetch the value from that reference, and they will feel accomplished, and that's where the laughter comes from. And your goal on a stage is to give them a reference that they can fetch the value for. If you give them the value directly, they will say this is not funny. This is too direct. So your goal is to give the references that 80% of your audiences can fetch and feel accomplished, and the end of that will result in a laughter. And sometimes you give them a long reference or a reference to a reference, and you say I didn't connect with the audience, and you get a segmentation fault basically. So yeah, that's how I got into it, and it's an interesting process. It did get me an upgrade one time.
What happened?
during a flight. So I was on sitting waiting for the plane to arrive at the gate, and then they delayed my flight a couple of times in a small increment. And so it was a Delta flight, so I posted on Twitter that so my flight got delayed multiple times in a small increment. I am flying Delta. I guess it's in their motto that we delay our flight one Delta at a time, and I tagged Delta, and they replied, and I got an upgrade.
Oh, that's funny. Manish, so I think from what I can see, you're able to connect references in computer science, pointers and references, such a fundamental thing, to the world of comedy and how people react, right? This is something that I think comes naturally to you. Or did you realize that after taking all the classes, or did comedy come naturally to you as a computer scientist?
I don't know. I think I think if I see a pattern, I like patterns, I like structure, and computer science is science and art. I think like comedy is also science and art. Not all of it can be decoded. Like sometimes something is just funny. Many times something is funny because there is a reason. There is a juxtaposition or a reference or like a simile or exaggeration. So
understood. You seem to have enjoyed that process. Manish, coming back to GPUs and specifically Nvidia GPUs. Now, you've worked on multiple generations. So you've done work on the V100, and then you worked on the H100 as well. And you've had this vantage point where you've seen multiple generations come over a period of time. What are the biggest architectural advances? What is happening that is enabling all this boom in AI?
I mean, there is not just one thing, right? There are many things that are coming together, and like many people are talking about it. So it's compute is getting faster. We can get through the data more quickly, more efficiently. We have these new generations of GPUs, and then there is like such a huge like computational boost every generation, from V100 to A100 to H100, and now in Blackwell. And it's not just that. As I said, it's not just about matrix multiplication. There is advances happening in how do you program these chips, how do you move data at different levels in these chips, and how do you create bigger data centers, and how do they communicate. So I mean, there are advances everywhere. So like I maybe I can just talk about what is happening the things that are closer to me. If you look at like before Volta, like it was Volta was the first chip. The tensor cores were introduced. Now you can your cores can directly multiply matrices instead of vectors, and then you can multiply bigger matrices on A100 and bigger matrices on H100, and now a bigger one on B100. So just one single instruction has gotten bigger, and then you have introduced different levels of memory, and then the way you move the data, you have put in some things in the hardware like out of bounds check. Like when you're reading from the memory, you're getting some intermediate memory. So now out of bound checks on Hopper could be done using the tensor memory access. So there are advances happening like everywhere to make this pipeline faster, and then the application came along, and then the results are coming out. These things are not outputting gibberish anymore. Like there are still many problems to be solved, like hallucinations and others. But these things like understand. Like it's so amazing that I am making some sounds and you are understanding it and then you are responding it. Just if you think about it, no computers, just humans, the language. But now a machine can understand it and I can talk to a machine, and it's just it's just like we have normalized to this, but we don't understand how amazing that is, and how more difficult problems we can solve going forward.
Yeah, we take some of these things for granted today, Manish, but these are remarkable events, right? New applications and so forth. You were telling me the other day that your daughter, speaking some of her first words, right? And
yes.
We consider that as a remarkable event, right?
Yes.
But somehow we take the machines for granted,
yes.
right?
That is like seeing a language model trained in person, and many people have seen it, but it's still amazing to see it.
Yeah, so the model got trained in 1 year?
Yeah, she learned one word, no.
What did she say no to?
Do you want to sleep? No.
Okay. Are you sure that's the right word you trained her on?
I don't know. I think she learned it from us. She also knows this. Like when she wants something, she said this.
Okay. So she said.
I think no. She learned it in Hindi, so she said nahi, and then when she wants something, she says it in English. This.
So she's able to communicate. She wants this, and whatever you suggest, she's learned that she can say no to that. Okay. Very interesting, Manish. So then going back to the architectural breakthroughs, they're across the spectrum. So they are on the memory side, they're on the GPU architectural side, they are the units themselves, right? The capabilities, right? It used to be like double, and then FP32, and then 16 has been around. Yes. So the units themselves are changing, right? So, and they've been able to use the area while the size of the chip is increasing. Now we have this, Grace Hopper super chip, right? And within that increasing area, so they have die-to-die integration and interposer-based designs and chiplet kind of structure. Yes. But within those, then there is a tremendous integration that is happening, and better designs.
Yeah,
right?
Like you mentioned, I knew I will miss some of these. Like talking about it, even so, like this lower precision FP8, and on Hopper now we have FP4 on Blackwell, and then and these are all just within the chip, right? Across the chip, like networking has also gone. There's a lot of innovation that has happened in there as well. Nvidia has NVLink and InfiniBand to handle this communication on these large systems, and then they have software on that. It's not just about the hardware again. They have their libraries, which is like Nickel, and you can use that to tame these hardware. You have the software to tame the low level inside the GPU, and then you have software to tame the communication across GPUs. So software.
So what you're trying
without the software, these things are just piece of brick.
So what you're essentially trying to say is that the success that you see with Nvidia is not just the hardware, but enabled by tremendous amounts of software.
Of course. I mean, it's both. Like you have to have the hardware.
Yeah.
And you have to have the software. But people think software is easy, but software is hard.
Especially the lower level software that you write.
Like lower level software, and then the abstractions on top of it, maintaining the DNA of that software is even harder. Like it takes you're never done. you got the weightless multiplication, it's working full throughput, you can't just leave it there. You have to think about how do I structure it so that if some modification comes in the future, which I don't know right now, I should be able to make it in 30 minutes or 30 seconds or 1 second.
Manish, now you've contributed to Cutlass. You're one of the early engineers who built it. What is Cutlass? And you've talked about gems, but could you explain to our audience what is GEMS and what is Cutlass? I mean, I'm assuming everybody knows what's a matrix. Is there a matrix multiplication? But what is GEMS and how does it connect to it, and what is Cutlass?
I mean, GEM is matrix multiplication. Like GEM stands for general matrix multiply. If you go like by a definition, it's like the output D is equals to alpha times A multiplied by B plus beta C, where A and B matrices are getting multiplied. So that is matrix multiplication, GEM. And then Cutlass is a collection of header files which has these abstractions build from the bottom to top, where bottom is the Nvidia assembly or PTX, and you have that assembly wrapped in a C++ template. So when you have an instruction, you have some runtime variables that are going into that instruction and some compile time information that encodes that instruction. For example, a compile time thing would be the data type of that instruction and the shape that instruction takes, the layout in which the registers will be for this instruction. So this is the compile time information. The actual data that instruction takes to multiply is runtime. So there is some compile time information, some runtime information, and there is this PTX or the assembly string. So at the bottommost level, you have this string wrapped around in a template wrapper, C++ template wrapper, which has the information that this instruction takes at the compile time in the template arguments, and then you can basically you can use this template wrapper to place that instruction in your kernel wherever you need it, how many times you need it. That is easier said, but how do you do it? Is then you write that lowermost layer, and then you build the abstractions on top of it, so that you can create your algorithms on top of it. So that is what Cutlass is. And is that the only way to do it? No. There are you can build these abstractions in other ways, and I mean there are like amazing software like OpenAI Triton which are doing it another way, and then they are doing showing great results. And that's what Cutlass is basically.
And how does Triton do it?
So Triton uses MLIR, and you can encode this compile time information in this MLIR. MLIR stands for multi-level intermediate representation. So you can encode the compile time information in MLIR in various data structures that this compiler infrastructure provides, right? Like compilers have been traditionally doing this constant elimination, constant propagation, and all of this stuff. So you can encode that, and MLIR provides you like attributes to encode that. And what MLIR really does is it allows you to create the IRs very, very quickly. So you can represent your low-level IR in this MLIR. You can create it. It gives you a lot of you can create a lot of boilerplate in like just 1 minute and create a new IR. And then you can have that IR, map it to your lowest level, and then build your abstraction where your compile time information and runtime information is stored in these MLIR data structures, so that the top level programmer doesn't have to think about the low level stuff, and they can type their code in some IR that can be exposed using Python so that ultimately it will place an instruction where it needs to go, how many times it needs to go.
Okay.
So the goal is basically, if I can magically write low-level code for all the kernels I need or all the operations I need, I will get the most efficient operation for that architecture. So how do you do it? So yeah, these are the two approaches that you can take, and then you can do it for like any hardware. Like this is not just for like Nvidia.
Okay. So Manish, it seems that your work is pretty involved. You have to understand the hardware at a very deep level and then be able to write scalable code. So recently Meta laid off a few engineers, saying that their AI works as good as an entry or a mid-level engineer. Is your job under threat? How do you see this going and the role of AI there?
That's a good question, and I have thought about it. I think yes, it was earlier a thought that only the creative field is what AI can do best, but I am coming to a conclusion that that if anything that can be provable, like mathematical, programming, math, and these systems will have a better chance learning that, and especially with if you give them reasoning, and if you give these machines like a sandbox, like right now it's just predicting a token and the token is out, and if it's wrong it's still out, but if in between it's writing some kernel code, and the reward for these machines is that first they have to be functionally correct, and then the machine figures out, given my spec of the machine, this is my domain of functionally correct kernels for this operation, and now within this functionally correct kernel my next set of rewards is the latency has to be as minimum as possible. I have to hit the peak flops, and it has all the textbook information from the architecture books and all the existing architecture for that, and then it has the ISA information and it has the sandbox. They can do it. I think so. They can do it.
For people who are building these kind of AI systems and using GPUs, the learning curve seems to be pretty steep. You did say that the machines are figuring it out, though, right? And you feel that they are going to be able to figure out, given enough information and the right metrics. But meanwhile, while they do that, how does one learn parallel programming and become good at it?
I mean, answer is the same, which will be like 5 years ago. There is a lot of information on web. Now you have these assistants as well that can teach you. Like you can pair up with any of these AI assistants, and then you can write your first code and then give it to it and learn with them. I would say pick something from the open source and start contributing. I mentioned 2 of the projects which are in there, like Triton and Cutlass. I think Triton would be easier to start with if somebody doesn't have any GPU experience. And then it's up to you how much low level you want to go. Do you want to just write at the higher level and leave it out there? There is nothing wrong with that, because if there are problems that needs to be solved just at this level, where you write some kernel code in Triton or in Cutlass, and then just creating that, and then not going to the lower level of PTX, just getting that right, getting some performance, getting some new operation that you want to validate. So you can start there and go low level, or you can, if you want to be a ninja, then you go into the PTX spec, you go into the spec of these new machines. It's like for Hopper and Blackwell it's published. You can go in Cutlass code base and into the Arch folder, and you will find all of these instructions that are new and useful, and then understand them and then try to build from the bottoms up. So these are the 2 approaches, and then I would say it's not easy. Get yourself closer to the experts. So join a team.
So working with people who are doing similar work, and then looking at and spending the time at the detail. Is it easy? Are GPUs developer or programmer friendly, or are there a mystery that they need to be unraveled working with them?
Like working with the people or working with the software?
The software, the people. Are GPUs developer friendly?
I mean, the Nvidia stack is, it can be improved, but it is more friendly in my opinion compared to the others. So you can start there. There was a nice analysis by Semi-Analysis, I believe, which is also sharing similar sentiments. So it's I would not say like it's easy. There is a lot of information you need to absorb, and you have to spend time and take a look at it. Take a look at the low level. Take a look at the high level. Whichever part you fall in love with, just keep doing that.
So for the longest time, Manish, we had the free lunch in software where the machines just got faster and faster, and you were writing a C code and you really didn't have to care about what's happening in the architecture. Is that world ever going to be true in GPUs? Because it seems that you are actually, at least for the kind of work that you do, you're really playing with at the register level, at the memory unit or the memory hierarchy level, and then the functional unit level, right, and its capabilities, right? Do you see that happening, or we are actually moving closer and closer to the hardware, away from the free lunch? But I think the eventual hope is that AI still is able to figure that part out, right?
I mean, AI can able to figure that part out if AI has that data. So it's like, that's why I think inference time compute is going to be even more important. Like Nvidia or Cerebrus or Grok is not going to give you their latest kernels. It's their business. So they have to learn on them at the inference time, and then make these models work with this new instructions, and then figure out what kernels to be written with that. So that has to take some time, but I think it's there. It's very close. We have to see it from our eyes when it happens, but it seems close to me based on the world I interact in. It's not easy, but it's developer friendly in the sense that there is a lot of information that is out there that you want to learn. But I think the best would be to, if you're starting out fresh out of college, the best would be to get yourself closer to the experts and explore some open source projects.
So Manish, you've worked on developing infrastructure for LLaMA at Meta. So essentially scaling LLaMA, there's this massive model that is out there trained on I don't know how many trillion tokens, right? Now, what are the core bottlenecks in scaling these very, very large models, especially on the training side, and how do you address them? On one side, you have all these GPUs, and then on the other side, you have, say 20 trillion tokens that are going to be used to train this massive model. What happens there? What are the bottlenecks? How does that work?
I mean, there are many bottlenecks. Like, it was like a big team and a lot of people working on it. It's like you have so many machines working on it. You have power limitations. You have the stragglers, like some communication fails, and then you have stragglers in there. So there are many, and then these are the issues that needed to be solved. Like, for example, one particular thing where somebody like me has helped or done the work in this area is that, like scaling, you need to go to the lower precision data types. Like inference was in 16-bit, we moved it to 8-bit. So to do that, you are losing some accuracy, but how do you gain back that accuracy? So you have to write a new kernel for that, or you have to that's where the programmability comes into picture. Like you could have like a plain vanilla DF16 matrix multiplication and plain vanilla FP8 multiplication. The FP8 is running double the throughput, it's running faster, but it's giving you less accurate results. And that will start giving you like that will lower your like accuracy scores and your output, like quality of your output. So you want to run FP8, but you want to run it with quality. So you want to do some tweaks there where you have to do some scaling, and there are various scaling methods that you can do. Is like a regular vanilla matrix multiplication has like a scalar that is multiplied after the multiplication alpha to scale it, but you can have more scaling factors so that you gain back some of the accuracy that you have lost during the quantization. So so you can just think of it as more scaling factors. So, but there is row wise where you have some scaling factors along the rows and the columns, and then you have block wise where you have scaling factors for the blocks of the matrices. So you want to use this lower precision, but you don't want to lose the accuracy. So you have to write these new kernels. That's where I help. But there is lot of other areas which need it. Like as I said, like running it on a massive data centers. There are some straggler nodes, like some nickel issues are happening and in the communication fabric, and then some nodes are just failed checkpointing, so that you have to have efficient checkpointing. So if something fails, you have some state. You don't want, you have like ran it for 2 months, something fails, and you don't want to run those 2 months again. So you have to have efficient checkpointing at every stage. So yeah, there are a lot of challenges.
Manish, we have talked a lot about training today, but there's this whole world of inference, and there seem to be some very interesting new trends in inference, such as test time compute and reinforcement learning. Please tell us more about what these trends are and why are they important. For example, test time compute will begin there.
Yeah, I mean, it's interesting time. I mean, there is something new happening every day. So I think there is a recent talk by Ilya where he said that the pre-training, as we know, has ended or is ending. I don't remember the exact present or past he mentioned, but it's like we have consumed all the data that we have, and we are consuming it faster, and then the compute is getting faster. We are not generating as much data that is already out there on the internet. Although there are viewpoints that I have heard that we have to still consume the video data. We have only consumed the text data and tokens. But these machines can generate data, right, during the test time. You are right now predicting a token at the test time. You are predicting one token, and even if it's not the best token, you predict it and you put it out there for your user to read it and consume it. But what if during test time, instead of predicting one token, you can produce multiple tokens, do some reinforcement learning on top of it to, based on a reward, pick the learn from these multiple tokens that you have produced at the test time, and pick me the best token based on some reward function. So that's where the world is going. And it's basically shifting some of the compute budget from training to the inference time, because when you are generating more token, doing an RL at the test time, you will need more compute at the test time than you needed previously for just predicting a token, because now you are not just predicting, you are producing. You are not just predicting the next token, you are producing like a bag of tokens, and then you are trying to pick the best combination of those tokens.
And how do you pick the best combination?
So that's where the AI people will come in, and I will work with them to figure out what works best for them. Can I take it to a GPU, and can this work? Do you expect this trade-off, like if instead of this we can do this, like because GPUs can do this better, or whatever compute we use, they can do better. But one technique is like you can, instead of producing like one thought, you can produce multiple thoughts, and you can pick the best one from that based on some score. You can do like this reinforcement learning to for example, in the case of the kernel writing work that we discussed, right? It's like you can ask the model to write a kernel, and it may dump incorrect kernel. But if you tell them that here is the GPU for which I want you to write kernel, and here is the GPU, write that kernel, run that kernel, it has to run, and it has to run as fast as possible, and you have 1 hour to do that. So now it is not just producing the next token, it is producing a lot of tokens.
A series of tokens.
Series of token it has to produce even for one kernel.
Yep.
So it's not just producing one kernel that will fail. It will fail if, and then it will learn from that, because there is a reward function that it has to run functionally correct. It has to see the success at the end of the test, figure that out, and then after it figures out success for all the kernels that have figured out success, learn from those kernels, and then figure out the best combination of the instructions that will get me the best performance. Either it's there in one of those kernels or it's there in combinations of those kernels. So that's how you can think of the test time compute and reinforcement learning and sandboxing.
So in some ways, it's similar to what people do, right? You assign a task to a team and they come up with, each of these members come up with different approaches, and then they holistically evaluate all of them, and a day goes by and then they come back and say, we tried these things and this is what worked, right? So is that what, in some ways, it's an imitation of what happens, and that's why the answer is test time compute actually produces a good answer, right? Or, that's the reasoning models that they talk about, right? Is that the right way to think about it?
Yeah, I mean, I would say that is my understanding. Like that is they are working as like how we are working. I mean, in a sense that this neural inspired machines were like that, right? We have neurons and we have connections. Our neurons are much more complex, but it's the same way. Like we have like we learn all year and then we do a test. So in traditional schooling, so that could be like you're training for an entire year to write one test, and your test is closed book. So that is what we have been doing so far. But if your test is open book, you can go to the library, you can you have learned, and now during your test you're also exploring, and it's an open book test. You have 3 days, go to the library, read more books, you have the questions with you, you have learned what you learned, but you still have 3 more days to explore.
Yeah, the nature of questions that you can give in an open book test are very different, right? Yes. And much more powerful than and something that you track from memory, right? Yes. And that's what reinforcement learning and test time compute is enabling you, trying to solve much more deeper and more complex problems, right? Because you have the learning from the training, but then this small window of 3 days of time or whatever. Hopefully in this case it's 1 hour or 5 minutes,
no,
right?
It could be 3 days. I suppose if it can solve cancer in 3 days, why not?
Okay. That makes sense. We'll take that for sure. Interesting, Manish. Manish, you've talked a lot about GPUs. Mm-hmm. We also talked about all of these new companies coming up, custom AI accelerators. Are they going to overshadow GPUs? They're like at least 100 funded startups trying to build AI hardware today, and a lot of people claiming and making bold claims. Where does this go, and do you see GPUs remaining central to training and inference in the foreseeable future?
Like I hope that they do, that we get more competition and more programmability and more options. But the game is going to be the software. Like you can build the chip, but how do you build the software around it? How do you build the software infrastructure around it? And not just your software. Like there is a lot of work that has gone into PyTorch to make it easier to access the newest generation of Nvidia GPUs through PyTorch. So somebody has to do all of that work. So it's you have to build the chip, you have to build the software yourself first, so that you can iterate fast, and then you have to make influence the other third-party software, which are the entry points for your customers. Like a lot of people who are writing things on Nvidia GPUs, they don't touch Qt and Cutlass and maybe even OpenAI Triton. They write things in PyTorch. So whatever is your hardware, it has to go into things like PyTorch and JAX and all these other things.
The infrastructure that the model and the inference application people use. So that's what's the background. Again, I think this has been a recurring theme, that it's not the hardware or the software is a very important component to it. Okay. Manish, towards the end of our interview, looking ahead, you've spent the last decade or so, more than a decade, about the last 15 years doing lower level programming, optimization, and then all this remarkable work on optimizing for GPUs and enabling this AI revolution by making very key contributions, doing all the early engineering work that's been behind. And I know your work and the work of your colleagues is now used by every major training company as an example, which is very remarkable. What are you personally excited about to tackle in AI? If you could solve one major problem or bottleneck, what would it be?
I think the major themes remain the same, is that you fall in love with a problem and then live with it and then hopefully solve it. And so I am excited about that. This new team at Magic that I am working with, there are new problems and new challenges, and like making these long context work, and then we have like variations to the model, and we have new models that we are trying every and then to try the new model you have to write new modifications to the kernels or new kernels to enable them on Nvidia GPUs. So enable that and see, and then like to make that work is what I am excited about at the moment.
So essentially, Manish, then it is getting everything to work, right? So you have this, you're now essentially trying to apply long context. Can you elaborate a little bit on what is long context?
It comes down to like these things go together, like test time compute, long context, and reinforcement learning. So long context is like right now the attention mechanism can only know like some tokens in its window, like it could be like 8K, or like there is 1 million for one of the variations of Gemini, 1 million token. But imagine if you can have like a larger context window of 100 million tokens. So now during the inference time, you can use some of the data, a large amount of data that you can use, like 100 million tokens to learn from that. So for example, I don't know how factual this number is, but say suppose PyTorch is 40 million tokens, and you can give the entire PyTorch repo along with its not just code, but its commit history, the people who have added the code and the issues, and then the text and who answered what, and you can give all of that information during the inference time. And PyTorch, this information can be given at the training time. So inference time will not be that important, but imagine some internal proprietary code base that any of these companies have. So they can give their internal code bases as this large context to already trained model, and then learn all of that, and now they can create new software using it. They know that these are the experts in this area from the commit history and the issues, and not just experts. If you pair these two people together, you will get something amazing, because most of the innovation comes not just for one person. It is basically like a small team working together.
Okay, understood, Manish. So what you really again want to enable through all of this, and what you're really excited about, is engineering all of these new key concepts. Training has been there. The world of inference is changing. That is your current focus. Very interesting, Manish.
And then I want to add, now at Magic we are a small team, and then we are all in one place, and I am closer to the people who are doing this model work. So it's that is also an exciting part for me, to see this model change from like 1 feet away.
One of the things you've said is to be with the right people and learning from them while you put in that time and effort.
Yes.
Manish, very interesting. Thank you so much for being here today. In this episode, we talked with Manish. Manish is a leading authority in AI training, GPU performance, compiler optimizations. Manish told us a lot about how GPUs optimize things, what happens in the world of training, and then very interesting new trends around test time compute and inference and long context and reinforcement learning. Those are new trends that will shape the future of inference as well. Manish, thank you so much for being here.
Thank you so much for having me.